In this tutorial video, I will introduce QPCED, a computer software for quantification and processing of polycrystalline electron diffraction patterns. You may download the software suite from the website on the screen. A paper about previous version of QPCED 2.0 was published in Journal of Applied Crystallography 2012. Here is the Landyne launcher icon. Click this button to start QPCED. Let me briefly introduce the function on the menu bar. For file include load electron diffraction pattern, load electron diffraction profile, save the analyzed result, exit. In process, this is pattern adjustment. You can resize the diffraction pattern you load. You can align the incident beam to the display area center. There is circles for guide you to do the alignment. This is ellipticity. You can check the ellipticity in diffraction pattern. If you need correct them, the program can do the correction to make it a full circle. This is enhancement. You can display your diffraction pattern in different pseudo colors, or you can find out strong and weak diffraction ring by use the maximum intensity profile. And there are various of display method here. In pattern, the first choice is ROI and TIFF. ROI is region of interest. Inside this area will be saved. Quantify. And the quantify, this is the main functions in QPCED. First is calibration. You can use the scaling bar to do the calibration. To convert the 2D diffraction pattern to a profile. You can convert the pattern to a line profile, or along one selected ring to show the intensity profile. Then there are two ways to search for the background and subtract it. This is for the peak analyze to find perfect match for the peak function. And you can adjust the overall height of the peak. You can also do the intensity normalization. After you get the intensity profile, three types of profile you can save. You can save the electron diffraction line profile. It's in blue. You can save the integrated profile, and you can also save the neat peak profile. In help, it gives you a function of current drive and serial number. You may load the electron diffraction patterns, use the window file system. In experiments, QPCED, click here. You can also use the drag and drop function. And just hold mouse left button, drag, and when you see the move, drop it. Get the same pattern here. Then we need to resize the pattern, slightly adjust the pattern, and also align the pattern, move the incident beam in the display center. You click this slide bar and you can use the arrow key to move up. Now the pattern is perfectly aligned. You can check all the ring. After careful alignment, we can see the two profiles, the blue along the blue line slightly outside compared to the red peak. Both red peak are slightly inward and blue peak outward. We use the radius mark to measure these two peaks in pixels. Suppose this is for the blue one is larger, we shall put the longer axis here. That will be 142. The red peak will be 141. In this case, we don't have a tilt angle. Later we'll show when we tilt the angle what happened. And we can calculate the ellipticity. This one gave the number is here. The tilting angle is 0, so azimuth also 0. So we can correct the pattern. After we correct the pattern, you can see the red line and blue line are in the same radius. When we make alignment, we make sure the horizontal and vertical profile in exactly 0 and 90 degrees. But when we do the ellipticity correction, we can tilt these two skin lines. This correction can be done for the ring pattern. Can also treat the diffraction pattern from single crystal. Those are from the same microscope, same condition. So calculate the ellipticity and use that number for all the patterns you get from the same microscope, same condition. The second application of QPCED3 is to enhance the diffraction ring with a marker and the pseudo colors to make diffraction rings more revealing. After the correction and enhancement, we want to print out the diffraction patterns. You can show the enhanced line or remove them. In pattern, first is ROI, then is the teeth, is the PPI, is the point per inch. If you go to pattern, save the pattern as T, or you can save the pattern in JPEG. We can also remove the horizontal line and vertical line. Here, you'll remove the horizontal and vertical line. The next is the main application to quantify diffraction ring pattern. We can get the intensity distribution along the selected ring. This is used for detect any implant texture. We'll choose this one. The second one is integrate the intensity along the ring and find the distribution from the center along the radius. We'll first do calibration, then we'll do along the ring, then do the whole pattern. The calibration dialog is in quantified. We also need the adjustment dialog, which can show and adjust the guide ring. Now we have the green ring selected, the first ring, and it reads as 141. We type here, and we know this is FCC aluminum. The first ring is 111. The D space is 2.3381 angstrom. And then update. That's the calibration is. We may select one of the ring and get a profile intensity distribution along the selected ring. First, uncheck the guide ring here. Go to quantify pattern and the profile conversion. And this is the ring. We have a radius and a width. Show you the width. This is large, and this is the smaller one, suitable one. And we can choose the radius. For the first ring will be this one. Then make the convert. And here you see is random distribution is the height of the intensities. If we have a in-plane texture, the intensity will drop at a certain point. And this show is fully random distributed ring. Same thing that you can get the other rings distribution. The profile of integrated intensities along the radius can be generated. We need a selected pattern, then click on the convert. The beam stop here will simulating in the real experiment if you have a beam stop on. Here both orientation and the width are 0. Let's increase the width. So you can simulate how large the beam stop in your experiment if you have beam stop on. And here to show the orientation of the beam stopper. Since we don't have a beam stop here, I can turn this one to 0. To remove the effect of the incident beam to the intensity profile, we need to go back to the pattern adjustment. This is the profile along the horizontal and vertical line. Now we go back to this dialog. This is the radius of the incident beams. We're going to increase it. So you can see from here and also from the brief profiles here will be cut off in the patterns. There are no information of intensity distribution inside this disk, so we can make it even bigger. Here this line is tracking down how the incident beam affected to the distribution of the ring. So we have other 3 parameters: the height, the full width at half maximum, and the ratios to simulating the position of this line. Try to close as possible to these curvatures. So the background curvatures best simulate on lower part. We can increase the cutoff. By now, the most part of the effect of the intensity distribution is covered. Then we can do the convert. And you can see this line is intensity distribution from the center to the side after we remove the effects of the incident beam. Now we're going to define and remove the background intensity. Let's go to quantified background. And you see the intensity profile is transferred to the main display screen. And we can lift the intensity up. Go to peaks, lift up. There are two ways to define the background intensity. The first way is called the Bruchner method. The only parameter is step and try and to see how it fits to the background. The second way is linear interpolation method. Define point. The point will be joined together to form a curve. We just try the first method. This curve shows a little bit over, go to the peaks. Let's try 50. It looks much fine. Define the background intensities and remove the background. Now we have the pure peaks here. Next step is define the peak positions. Here you have an automatic search method, or you can identify manually by clicking on the top of the peaks. We try to search, and here it gave us 7 peaks. 1, 2, 3, 4, 5, 6, 7. There must be one peak defined more. 1, 2, 3, 4, 5, 6. Only 6 peaks, but here listed 7 peaks. Let's try to see where the 1 peak we may need to delete. This one look species is the height only 1. Position in 646, and here are the position to show 650 around here. So there are a small peak defined here, which is certainly is not true. So we selected, we can delete number 6. It didn't affect here because that peak is very small. Delete, you can delete here and select the peak, or you can delete from the table. If any peak you didn't find, you can add also. Next, we have a refine the peaks. We have a two peak function. It's a pseudo Vogel and Pearson 7. You just try the first one. Always try the first one. If it didn't work, try the second one. We'll click here. Refine the position and also the height. It calculated D-spacing too. Also use the calibration we defined earlier to calculate D-spacing. Still the intensity not defined. Here we have a right click of the mouse. We can show the peak as a bar or overlap superposed. And you can see it defined the peak perfectly. And this one you see is a little lower because they are superposed. And this one also lower. The last one is show the overload composite. They will trace the experimental data perfectly. So normally we just show the second one, overlap superposed. If the refinement is not going well for some special case, you can always do the adjust by one. So you click here, you give the position, height, and its full width at half maximum, and the ratio of Gaussian and Lagrange ratio. And you can choose which is the peak number. Here it is. So this is rarely used, but you can define them. After refinement, we can get normalized intensity and also the lattice spacings. Could quantify, normalize the peak of the intensity. This peak is 100, and the rest peak are shown here. We also get the lattice spacing here. To show the overlap computation, we can see the difference of calculated one and experimental one here. The difference is very small, close to the horizontal line. Thank you for watching. Please check our other videos about Landyne software suite for electron diffraction simulation and crystallographic analysis.